Hello and welcome to week 12, lecture 1 of CO 442642 graph theory. Today we'll be discussing flows. What are flows? Well, to do that definition, we'll need an understanding of directed edges. So let me use some notation. Let E of G, but with a vector hat on top, be the set of kind of directed edges. So EXY triples, where EX equals XY is an edge of G. Why do I write this instead of XY with just a vector on it for direction? Is because we will be discussing today multigraphs. So everything, even though it seems to be phrased in terms of simple graphs, really it's phrased in terms of multigraphs with parallel edges and or loops. And so if you have parallel edges, then we need to have an understanding of the different edges. So there could be many pairs x, y, and so we'd use this notation. But I'll kind of gloss over that, but you'll see where it's used in some of the proofs we'll do. So we'll be doing directed edges, that's some notation. Then here's kind of our first key definition, is called circulation. So if G is a graph and H is a finite abelian group, then an H circulation is a function f from these directed edges to values in H, such that the value of an edge in one direction is equal to the negative of the value in the other direction. And again, negative or inverse is a well-defined concept for groups. And then the other thing we have is that the sum of the edges around a vertex, so E equal xy, again that's over maybe multi-edges, the sum of all of those should equal 0 for every x in V of G. And you can see there where we're using the abelianness, the commutativity, because then the sum is well defined. So those are the two big things. We'll also call H circulation. So this is natural. It comes up in modeling various network type flow problems of water, of transit, traffic, mass, all that, that you want to apply values of a sense of flow for each edge. So then you need direction. Of course, kind of the flow in one direction is the negative of the flow in the other, if you think of it as like a net flow. And then the second point is that the flow in and out at a vertex should be equal, should be 0. And that second condition is called Kirchhoff's law, after it comes from electrical networks. So these are the two conditions of circulation. What is a flow then? The flow is, well, an H circulation F is called nowhere 0 if it's nowhere 0. So if F is not equal to 0, and 0 being the identity of the group for every edge. And then we call such an H circulation an H flow. So this will be our terminology as coming from Diestel, that we have kind of circulation if you satisfy the inverting property and then the sum property, this Kirchhoff's law, and only call it a flow if it's actually nowhere 0. Now this is not standard in the literature. Generally circulations are referred to as flows, and flows are referred to as nowhere 0 flows. But to stress maybe the difference and not have to continually say nowhere 0 everywhere, we will just use this notation. So circulations, which we'll study less, and flows, which is what we're really interested in. Why is that? Because it's not so interesting if you just allow things to be 0, because then you could just set everything to be 0, and that would be a circulation. So circulations aren't as interesting as flows themselves, where you have this nowhere 0 property. So that's our basic definition. And note, again, this is with finite groups. So here we're just thinking, cyclic groups, things like that, abelian groups, instead of actual numbers. We'll come back to the idea of actual kind of numbers and using the integers and such. So we'll get back to that, but let's just work with group flows for the moment. I want to point out some properties of circulation. So it will be useful if x and y are subsets of E of G, and here they don't have to be distinct, to let this E vec of xy be the EXY triples, where x is in x and y is in y. And then, so, you don't need x and y to be distinct. Indeed, they could be equal, and this would still make sense, because we have kind of a direction, right? We have x's will be the fronts, and y's will be the backs. And then we'll let f of xy be the sum of all the values of such edges. So kind of the flow from x to y, you can think of it as. And then Kirchhoff's law is actually equivalent that f of x vg is 0 for all x. So the flow out of a vertex should be 0, that net flow. All right, and what else can you prove? Well, here's a nice little proposition that if f is an H circulation of G, so G is a graph there, and x is a subset of the vertices, then f of xx is 0, and f of xvg is 0. And I ask you why, so again, pause the video if you want, and think a moment, why do both of these properties hold for any subset x? So now that you're back, I'll cover the first one. It's equal to 0 because you're counting edges in both directions. So what's fxx? We're summing up the flow kind of within x, right? So that's edges with one end in x and then the other end in x, but you're going to count every edge in both directions. You're going to count xy and yx, and so then you end up with that canceling out, and then the whole thing sums to 0. So that's just using the symmetry property of flows. And then the other one follows from Kirchhoff's law, right? So the flow out of any vertex to the rest of the graph is 0. So then if you're just summing up all of those things, you can make them each 0, and so it sums to 0 as well. So the second one is by Kirchhoff's law. All right, so that's some basic properties of circulations. We will move on then to talking about generally what are called flow polynomials. So here's the idea. If G is a graph and H is a group, we let PG of H, and this is really standard notation, but denote the number of H flows of G. So we want to count them. Now you might say, why do we want to count them? Do we even know they exist? Well, actually, that's kind of the point. If the number is 0, then they don't exist. And amazingly, what is true is this very nice result of Tutt from 1954, that not only can you kind of figure out this number in a way, that actually this number is related to a polynomial, that there, for every graph G, there exists a polynomial PG of x, such that for every finite abelian group H, this PG of H, the number of H flows of G, is equal to that polynomial, evaluated at the size of the group, evaluated at the size of H. So why is that a very nice result? Because it has a nice corollary, right? It says that for every graph G and group H, the number of H flows of G depends only on H. So it's nice that you get a polynomial, but maybe even nicer that you actually get that the number of H flows of G depends only on the size of the group, which is a bit surprising, right? I mean, there can be abelian groups of the same order there, but it doesn't depend on the group structure, only the size for the number of such H flows. So that's quite nice, right? The group structure doesn't appear. It's more of a graph theoretic thing than a group theoretic thing. And an even in particular corollary of that is whether you're non-zero, right? So if an H flow of G exists for any finite abelian group of order K, it exists for all of them as a consequence of that, right? That it's not, if it's non-zero for one, it's non-zero for all, and actually the number is equal. So this is quite a nice theorem. So basically, it's nice about the polynomial, but maybe it's more interesting, this corollary, that the number only depends on H, or that it only if they exist. But the key is we're going to actually use that polynomial property to really prove it. So that we'll do this kind of accounting with the size and show you that it only really depends on the size. And that's what will show up. So now, how will we do that? Well, to prove it, I'll first prove you a nice little lemma involving contraction and deletion. So maybe you've seen something like this before. If you end up taking matroid theory, you'd see this. But here's the nice idea. Let G be a graph, and if you have an edge E that's not a loop, then it turns out this PG of H, the number of H flows of G, is equal to PG that's G contract E of H minus PG minus E of H. So the number of flows is related to the number of flows in the contraction minus the number of flows in the deletion. Okay, so that's going to be our key lemma to proving the polynomial one, because then we can kind of use it inductively. How do we prove this lemma? Well, let fg of h denote this actual set of h flows of g. So pg of h would be the size of that set, of course. So let's study this actual set of h flows. What do we get? Well, we get that it suffices to prove that fg contractee of h is in bijection with fgh union fg minus eh, right? So if you just move the negative term there to the other side, you could see that if we could actually prove this bijectively, this equality. So to do that, let's study an edge equal uv and consider an h flow of g contractee. So here's a picture of it. Here's an edge equal uv. I've contracted it in the right-hand side there, and then, so we had 4 edges and 3 edges, now we have 7, and I've gone ahead and put some kind of flows on it. So maybe this is from Z3 or Z5 or so on. And then what do we have? So, and you'll notice it satisfies Kirchhoff's law, right? There's kind of 5 coming in and 5 coming out, so that should balance out to 0. So, imagine this is from some wider flow, but I'm only looking at it locally at the contracted vertex. And what you can see is what happens if we take this flow and bring it back out to kind of a flow of G, like uncontract E. What happens, so here's the flow on the right that we had, if I uncontract E and put the kind of half edges there with their values, what will you notice? Well, you'll notice that the values around you will sum up to some number. So in this case, it's kind of 3 incoming, or minus 3 as viewed from the vertex. For V, it's 3 outgoing there, so 2 and 2 minus 1, which is the opposite number. And that's actually how it's always going to be. So the idea is that there is then a unique value for E to actually get the result to be a flow, to satisfy Kirchhoff's law, right? If U has 3 coming in, then V has to have 3 going out. So how can we make it so U and V have 0? We should flow that amount of flow from U to V. So here in the picture, we would send 3 from U to V. We'd orient the edge and put a 3 on it, as depicted, and now U will end up with flow 0, and V will end up with a net flow 0, and thus we'll have gotten Kirchhoff's law. Now what can actually happen though, so there we actually mean not flow, that's a typo, I mean as kind of a circulation. Because the issue is whether or not it satisfies nowhere zeroness. But again, so it's well defined. You can take f of EUV to be this negative of the sums of the f's, just as I wrote there, but also for example in the picture. And now there's 2 cases, as I suggested. There's one where f is 0. So in the picture I had it that the number was 3, but it could be that they already summed to 0, and then you don't need to put anything. Well, that's exactly the case then that what we have is already a flow of G minus E. And then the other case is that it's non-zero as depicted, then you'd actually get a real flow, an H flow of G. So that's the idea, is you expand, there's only one choice if you want to keep Kirchhoff's law to make it a circulation, and then what happens is either that choice is 0 and you get an H flow of G minus E, or it's non-zero and you get an H flow of G. And you can see that this is actually goes both ways. So if we had such flows, you can contract and indeed get flows of UV, and this thus establishes the bijection. Okay, so that was our proof of the contraction-deletion lemma. This proves the lemma. Now we can prove the flow polynomial result. So how do we do that? Well, we do it by induction on E of G, which is kind of what I've suggested. And then there's the case that if you have an edge that's not a loop, then by the deletion contraction lemma, we know that the number of H flows of G is related to those of G contractee and G minus E. Why is that useful? Both of those graphs have fewer edges, and one you've deleted and the other you've contracted an edge. So by induction, there exist polynomials PG contractee of H and PG minus E of H with the desired property, namely that they are polynomials and that the number of flows is equal to the polynomial evaluated at the size there. So that's good. So we have the existence of these polynomials that work for all H for the smaller graphs. So then we would just define PG of H, our new polynomial, to be the one given by the deletion contraction formula, and that would be a desired polynomial, as the difference of 2 polynomials is a polynomial. Okay, so that concludes the first bit, that if you had an edge that's not a loop. What if every edge is a loop? So this is the next case. Every edge is a loop. What do we do then? Well, here's a picture of kind of a graph where edges are loops. Basically, every component ends up becoming one vertex, and there are loops there in each, around each vertex perhaps. So now what do we do? Well, now the idea is I just can actually count. I can count the number of H flows. Why? Because any assignment of non-zero values in H to these edges is an H flow of G, right? So for every edge, I think of a direction, and I'm in that when I've kind of directed it, I can pick any value from H as long as it's not zero. And that will maintain Kirchhoff's law because it's a loop. The flow going out comes back in. And so then it's easy to count how many flows you have, what PG of H is. Namely, there's H minus 1 choices for each edge. And so we raise that to the number of edges. And you'll note that's a polynomial in the value of H. And it's a polynomial as desired, right? It works for every H, only based off of the size. So that's kind of the key idea of this theorem of Tutt, is the non-loop case, there's this deletion-contraction relation, and in the loop case, it's clearly just depends on the size of H. And so, you could put in more work to actually figure out what the polynomial is going through this deletion-contraction. It gets a bit messy, but we don't care. We just need, in the end, it's a polynomial that depends on H. Okay, so we've done that, and maybe you can appreciate where the polynomial proof is nice because we don't really know with the minus thing whether or not the numbers might cancel out. So it's a little hard to do it just by existence and non-zeroness. We really need to count the number of H flows. All right, so that was Tutt's proof, and that's established this nice thing about group flows, that it doesn't matter what the group is. But this gets us back to something else I wanted to talk about, which is maybe more natural than groups, is something called k-flows. So let k be an integer of at least 2. A k-flow is a function f from e of g to 1 up to k minus 1, such that it has the symmetry property and the sum is 0. And I should say a third property, it's baked into the thing though. You'll note, so pay attention, 1 up to k minus 1, so it's nowhere 0. Right, so in the literature, this again would have been called nowhere 0 k-flows, and they would have allowed 0. Here, we're going to assume they're not 0. So we're kind of allowing the numbers 1 up to k minus 1. The kth element of the group would have been 0, but we're going to disallow that. And again, the idea is so then you should also allow negatives. So I mean that at least one of the directions gets sent there, the other direction gets sent to its negative to preserve the value. Okay, so that's what a k-flow is. So it's an assignment of these values 1 to k minus 1 that seem to satisfy the circulation properties and is also nowhere 0. And the question is, are these related to zk flows, for example? They seem very close. So look at this picture, for example. Here's a small graph, a K23, and on the left side, I've drawn a Z3 flow. So I directed out all the edges 1, then they kept going 1, and this is actually a Z3 flow. Why? Because, it satisfies symmetry if you flip them around, but also what you get is that the sum at each vertex is 0, but 0 modulo k, and k here would be 3. Right, so the interior vertices, it's clearly 0. The top is kind of negative 3, and the bottom is plus 3. Where on the right side, I've gone ahead and drawn an actual 3 flow. So that's the crucial difference. So here, I kind of flipped that path on the left side. So instead of 1, 1, I flipped it the other direction, went 2, 2, and now everything is really 0. So it's 0 at top, 0 at the bottom, and 0 in the middle. So that's the key kind of difference between a k-flow and a zk flow, is this concept that, a zk flow, it looks like we're assigning the values 1 up to k minus 1, but there, it's 0 mod k, it's 0 in the group. Here it'd be 0 in the integers that we want. So that's the important thing to know. It's in that definition, that Kirchhoff's law as 0 in the integers. But amazingly, there's this nice theorem of Tutt, because the question you would ask, are these related, is, well, okay, could it be that you have to have one, then you have the other? And Tutt proved this in 1950. that a graph G has a zk flow if and only if it has a k flow. So the two are related. They're obviously, I've shown an example where they're not exactly the same thing, but the existence of them is tied together. So why is this? Well, one direction is obvious. Do you see which direction? So go ahead and pause again if you just want to think through that definition. But which direction is obvious? If G has a k flow, then that is a zk flow, right? So on the previous picture, my flow is actually still a zk flow. If I only view it as the 1 up to k minus 1s, then that is indeed, if I'm 0 there, then I'm 0 mod k. The other direction, though, is the problem. We have to show the reverse. So namely, we have to show that if there's an assignment of values in k minus 1 to the edges, here I'm directing, and of course you have the negatives in the other, such that the sum at every vertex is 0 mod k, as in that first picture, then I have to show there is such an assignment where the sum at every vertex is actually 0. So the picture from the left side, I started with 1, but Z3 flow, but at some vertices it had multiples of 3, positives and negative. If only we could turn that somehow into 0 everywhere. That's what we have to do to prove this theorem of Tutt's, which is quite remarkable that this ends up working out, but once you see the proof, you'll come around to why this should be true. And the idea is essentially what I kind of did on the last slide, where I'm going to flip a path. I'm going to try to reduce the non-zero-ness of the Z3, or more generally ZK flow. So let's get to the proof. So what we'll do is we'll pick instead of viewing it as an algorithm, we'll of course get to a minimum object. So here we'll take a ZK flow that minimizes the sums at the vertices absolute value. So what do I mean by that sum? I don't mean as viewed as a zk flow, but as viewed as a k flow. So in that previous example, we had a +3 and a -3, so we absolute value those, and that would have started with a 6 for this value, but we want to get it to 0. So that's actually case 1, is if at every vertex, so we already summed to 0 perfectly in the integers, then we're just done, right? Then f is a k flow as desired. That's exactly what we need in the definition. So we can assume there exists a vertex v that is non-zero, and then if you think about it, because the whole sum is 0, there has to be one that's positive, right? So again, you should think of flow as mass, moving around. Kirchhoff's law is the conservation of mass, and so here, the idea would be, Zk is 0, but more generally it's not. So that means there are kind of sources and sinks. So, of course, if you have to have a sink, then you'd also have to have a source. So we could assume that there's this positive, this source of flow, V. Now what do we do with that? Well, let X be the set of vertices reachable from V by directed paths. And by directed paths, then I mean in the positive sense. So ones where flow is actually flowing positively. So think of everything you can reach there. I claim that there's a vertex X in that set big X that's a sink, that has negative negative net flow. So that should be pretty obvious to you, right? If I have a source, there must be somewhere where there must be some sink where that flow is going to. That's all that claim says, but we'll prove it anyway. So here's a picture. So here's X, here's V. Here's maybe the set of vertices that are reachable by these positive paths. I claim that there's this X, some sink. Why? Suppose not. What would it mean? It would mean that all of the vertices inside X are either positive, they're sources, or they're net 0. So that means the total kind of flow coming out of that set X is positive. X as a set is a source. Yet, f of xx is still 0. So even though it's not clear that we're a circulation anymore in the integers because we have sources and sinks, it's still true that edges have symmetry, and so then the amount of flow inside a set is 0. And so if you put that together, right, if I'm a source as a set and yet my flow inside, I don't create, mass inside, then it must be that there must be flow coming out. Must be flow coming out of X to V of Gx. So you can just work through the definitions of that, but that's what we get. And once you see that, that means there is an edge that's positive coming out of the set X. So this is what it would look like as depicted, say, if you ended up, doing it out, say if you wanted all those other vertices to be 0, you would notice kind of the top and the right one I've labeled y would have to have some edge coming out of them to make them not be sinks. And then that's a contradiction, right? Because then z, this new vertex z, is reachable from sorry, that's a typo, that should say v, by a directed path, a contradiction. So very good. That's kind of the idea is, if there was flow coming out of it, then we would have enlarged our set X. So again, just if I must be able to get from some source to some sink. That's all this claim is saying. And now that we've done that, we're almost done, because now we're going to apply our flipping trick. So let P equal WWM be the directed path from W0 equals V to WM equal X. So here I've drawn kind of a picture of that. And again, they're directed, so they have values of flow on those edges. They don't have to be the same. So A1, A2, AM there could all be, different numbers, but there is some kind of positive flow going from V to X. Okay, so that was what we had proved, and now we're going to apply this flipping trick. So we're going to construct a new K-flow F prime by assigning, I'm going to take all of the values of those edges, and I'm going to go ahead and subtract K from them. So I'm going to decrease them. Now what does that do? That means that I've taken all of these values that were positive, and I've subtracted K. Well, those values were between 1 and K minus 1. That's coming from the ZK flow. So what does it mean? That means they're now negative. So really, I shouldn't view it as this. I should view it as I flipped the edges, right? So now I've redone the picture where instead of kind of A1 minus K and A2 minus K, if I flip the edges, now I actually get positive. So they were positive, now they've all become negative. So really, I should view it as now the path goes the other way with values K minus A1, K minus A2, etc. if I'm only allowing you to direct in positive directions. So that's going to be a new flow. I claim it's a flow. Well, let's think about it. What is our new value kind of at a vertex? So again, typo, those should be, comma V of G, but F prime of Wi V of G should be equal to, well, it depends on the things, right? So everywhere else, of course, we haven't affected the flow at all, so it's going to be unchanged. Here, though, the key instance to see is that the middle vertices have the same amount of net flow as before. Why? Because you've subtracted K incoming and K Hermann outgoing edge, and so then those cancel out. Now, what happens at W0 and WM is, W0, you kind of have a negative A1 before, if pointing toward you, and now you have K minus A1. So what ends up happening is you have K more coming in. So your total net flow has gone down by K, right? I subtracted K going out. So my total net flow is now F of W0 minus K. And what about for X, also called WM? It's F of WM plus K, right? So all that we've done is we had this positive path, we flipped it by kind of now what happens is we ended up sending K new units of flow out from X along the path to V. So the amount that X had coming out of it increases by K, while the amount for W0 decreases by K. It's K new incoming. So what does that mean? It means that I get F prime to be a ZK flow. It's an assignment of values 1 up to K minus 1 on the edges, or they're negatives. And the sum of these absolute values is actually smaller. So the sum of these absolute values would actually be smaller, right? Because the key was that W0 was positive, and we've decreased it by K. And of course, I should say, it's obviously at least K, because it has to be a multiple of K. So it was some higher, some multiple of K, and I decreased it by at least one multiple of K. And X, which was negative, increases. So I'm balancing out the flow. Basically, if there was a source, I can find a sink, and I can direct flow back along that to counterbalance the negative with the positive. I keep doing that enough times, and then eventually I just have to get 0 everywhere. So that's our proof. That concludes our proof of Tutt's other nice theorem that zk flows, their existence is implied by k-flows and vice versa. So quite a nice result. So we've learned today about group flows, and that it really only the order of the group matters, and then we talked some about these more integer flows, and they're actually related to the group flows. So next time we'll talk some about which actually graphs have which kinds of flows, conjectures about that, and actually how flows are related to coloring. So until next time, see you then!